Section 9.6 is the fundamental counting principle, or is counting principles, but they all come back to the fundamental counting principle. Okay, so we're first going to consider the situation. How many outfits can you make if you have 6 different shirts, 4 different pairs of pants, and 10 different socks? So if you wear your red shirt with your blue pants and your white socks versus your red shirt with your orange pants and your gray socks, those would be different outfits. Okay, assume each outfit consists of 1 shirt, 1 pair of pants, and 1 pair of socks. Okay, so if I have 6 shirts, and I can match each of them with one of my 4 pairs of pants, and then I can match those with 10 pairs of socks. The fundamental counting principle says I just multiply the opportunities for each one, so 6 times 4 times 10 means that I have 240 possible outfits that would all be unique. Okay, this applies to other situations. So for B, it says the Nevada State Lottery requires you to pick 5 numbers from 1 through 30 for your ticket. In order to win, you must match all 5 in the correct order. Numbers can repeat. How many different tickets are possible? So this is also useful for when you're trying to gamble and it's not a good idea. Okay, so in the lottery, I have to pick 5 numbers. So I'm just going to leave 5 blank spots and consider them. Okay, so if I kind of think of it like the outfits, okay, for my first number, I could have anything between 1 and 30. So there's 30 possibilities for the first spot. For the next one, again, 30, 30, 30, 30. So there's 30 to the 5th possibilities. And if I put that in my calculator, that would be 24,300,000 ways to pull the 5 numbers from, I don't know, however they pick the lottery. Okay, let's consider example C. Okay, student IDs consist of a 2-digit number followed by 3 letters. So for example, it could be 27 and then it could be DAB. That could be an example of a student ID. The question is how many possible IDs could be made? Okay, so first let me think. The first 2 spots have to be digits. Okay, so how many possible digits could there be in the first spot? Or there could be 1, 2, 3, 4, 5, 6, 7, 8, 9, or there could be a 0, so there's actually 10 digits. There could also be, there's 10 possible digits for the second spot. It doesn't say the digits cannot repeat. Okay, now for the next 3 spots, they're going to be letters. Okay, if we're talking about the English alphabet, there should be 26 possible letters to pick from for each of these spots. Okay, so 10 squared times 26 to the 3rd when we put it in our calculator. There would be 1,757,600 possible IDs made. Okay, now let's consider our IDs again. Okay, this time for the student IDs, it follows the same progression, but you cannot repeat any of the digits or the letters. How does this change the number of IDs that are possible now? Okay, so I'm still starting with digits. Okay, now there's still 10 possible digits for the first spot. I could have 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Now, depending on what I pick for the first spot, if I put a 3 in the first spot, then I can't use the 3 again. So there's only 9 possibilities for the second spot. If I put a 7 there, I've used up the 7. There's still 9 possibilities left for the second spot. Now for the letters. Okay, there's 26 possible letters for the first letter spot, but once I use up one of the letters, I cannot use it again. So now I'm done at 24. Once I use 2 of the letters, I'm done at 20, 25, 24. Okay, I'm going to put this in my calculator. Okay, so if I add the restriction that the digits and the letters cannot repeat, we only have 1,404,000 IDs possible. So we lost 350 something thousand ID possibilities. Okay, the fundamental counting principle, or what we were just doing, relates to what we call permutations. Permutations of n elements is an ordering of the elements such that one element is first, one is second, one is third, and so on. So it has to be in a certain order, just like on the ID cards, they had to go in a certain order. Okay, the way we write permutations or using the notation is if we want to rearrange 10 items or n items into n spots, we would say npn. And the way we would calculate is n factorial. And I will show you why that is the case in the next example. Okay, sometimes you want to rearrange n elements, but only r at a time. So for example, maybe I have 10 items, but I only want to place 3 of them into spots. So I would say I'm 10 permuting 3, and this would be the formula I will use. I will show it to you in a second in example 2. Okay, so for example 2a, it says how many ways can you rearrange the letters in POTUS? Okay, I'm going to show you 2 ways to do it. One is using permutations and one is using the fundamental counting principle. Okay, so if I use the fundamental counting principle, there are 5 letters possible. These are just blanks. You don't need to write the blanks. They help me remember. Okay, there's 5 letters I could put in the first spot. I could put the P or the O or the T or the U or the S. Once I pick what goes in the first spot, there's 4 left for the next spot, 3 in the last spot. And then once I picked 4 letters, there's only 1 left. Okay, so there's actually 120 ways I could rearrange the letters. Okay, because I'm rearranging 5 items into 5 spots, I could also express this as a permutation. Okay, this is the same as 5 factorial. And if you think about it, that's the exact same thing as 5 times 4 times 3 times 2 times 1. I'm going to look for the factorial button on my calculator. And I still get 120 ways. Okay, so either way you like to think about it is fine with me. Okay, now I'm going to consider example B, and it's going to be an example of the permutation of n elements r at a time. Okay, so now I have 10 books. I want to arrange 3 of them on a shelf. Okay, so I'm going to do it using the counting principle, and then I'll do it using the formula. Okay, so there's only 3 spots on the shelf. 3 spots on my shelf. Now for the first spot, I have to decide between all 10 books which one I want to put there. Okay, now for the next spot, once I decide what goes in the first spot, I only have 9 for this next spot. And then for the third spot, I have 8 to pick from. So 10 times 9 times 8. There are 720 ways I could arrange 3 of the 10 books on a shelf. Okay, if I consider this like a permutation. Okay, so n elements are at a time, so I'm doing 10 p 3 because there's 10 items, there's 3 spots. Okay, according to the formula, it's n factorial at the top, so 10 factorial at the bottom. And then n minus r factorial at the bottom, so 10 minus 3 is 7 factorial. Okay, and if you think about this, if I have 10 factorial in the numerator, 7 factorial in the denominator, 7 times 6 times 5 times 4 times 3 times 2 times 1 cancels out, and what I'm left with is the 10 times 9 times 8, which means I will still get 720 ways. But if you have found the permutation button on your calculator, you could also use the permutation button on your calculator. Okay, now before we get to combinations, let's consider what your book calls distinguishable permutations. So how many distinguishable ways can the letters in banana be written? Okay, now if I'm thinking this is kind of like a permutation, it's kind of like the POTUS problem. How many letters are there? There's 1, 2, 3, 4, 5, 6. So it seems like it should be 6 factorial, but we have some issues here. Okay, now the issue is if I switch this A with this A, it's actually not a different permutation. It's the same because they're both A's. So I need to delete out all the possible repeated permutations that I have listed. So for example, for the A's, how many A's do I have? A, A, A. Anytime I rearrange those 3 letters, it's actually going to be the same permutation. So in order to get rid of those permutations, since there's 3 A's, I'm going to divide it by 3 factorial. 3 factorial is 6, so I actually have 6 times as many permutations as I should have because of those extra times 6 arrangements. Okay, now are there anything else? Yes. I also have 2 n's, so every time I switch the 2 n's, my permutation says that those are different permutations, but they're actually not. since there are two n's, I'm going to divide by 2 factorial to get rid of those rearranged permutations. I'm going to put this in my calculator, and I'm going to get that there are actually only 60 ways to rearrange those letters, and that's because of some of the letters that repeat. Okay, now we're going to consider combinations of n elements taken at a time. When you're doing a combination, you're taking like a group of items. So think of groups of things. The main thing to keep in mind is that the order does not matter. Okay, whereas in permutations, the order matters very much. It matters whether you're first, second, or third. But if a big group of people are going to go to the movies, it doesn't really matter whether you invite Joe, Anna, and Nancy, or Nancy, Anna, and Joe, or whoever I just said. It's groups. Okay, this is the formula. I'm going to show you how that is exactly like the distinguishable permutations, and then you can decide whether you prefer the formula or you prefer to think of it still using the counting principle. Okay, so for this example, it says out of a group of 7 colleagues, only 3 can go on a business trip. How many different ways can the groups be formed? So there are groups of 3 out of the 7. Because it says groups, I'm thinking combinations, but I'm going to do it first thinking of the fundamental counting principle. Okay, now there's 3 spots on the business trip. So I'm kind of thinking it should be 7 times 6 times 5. But if I do 7 times 6 times 5, I'm assuming that the order we invite the people on the trip makes a difference, which it doesn't. So I'm going to divide by 3 factorial because for each group of 3, the order didn't matter. So I want to divide by all the rearrangements of those groups. If I put this in my calculator, there's 35 ways the groups can be chosen. Now, if you're a person who likes formulas, you're going to look at this and say, I'm taking groups 3 at a time. So I'm doing 7, and I'm choosing 3 to join my group. Okay, and then I'm going to use the formula. Okay, according to the formula, this is n, this is r. So at the top, n factorial. Okay, at the bottom, we have 7 minus 3, n minus r factorial. And then we have r factorial. Okay, and you could plug this into your calculator and you would still get 35 groups, and we are going to stare at it to make sure that you see that it is actually the same. So if I do 7 factorial over 4 factorial, 4 and lower cancels, which means I'm left with 7 times 6 times 5, which is the same. I divide by 3 factorial because that's the rearrangements of my groups of 3. Either way you do it's fine with me. Just set it up so I know how you did it. Okay, now we're going to consider where there's more than one criteria. Okay, so in this case it says a kickball team has 12 members. It must have exactly 4 girls and exactly 8 boys. Okay, there are 10 eligible girls and there are 15 eligible boys for the team. How many ways are there to form the team? Okay, let me start with the girls. Okay, I want exactly 4 girls. There are 10 to choose from. So I'm going to do 10, choose 4. And I'm going to multiply it by all the different ways I can choose the boys for the team. For the boys, I want exactly 8 boys and I have 15 to choose from. So I'm going to do 15, choose 8. Okay, I'm going to put this in my calculator. Most of you have a 10, choose 4 in class. I will try to help you find it. 15, choose 8, 64, 35. Okay, so I got 1,351,350 ways for them to form the team based on the given criteria. Okay, the last thing we're going to think about is poker. Okay, a standard poker hand consists of 5 cards dealt with from a deck of 52. How many different poker hands are possible? Okay, this is a deck of cards. If you are not familiar with cards, they look kind of like this. The hearts are red. The diamonds are also red. The spades and the clubs are black. I don't know. We'll get to it later. Okay, a standard poker. What am I doing? There's a deck of 52. I'm choosing 5. Okay, so if there's a deck of 52, I'm choosing 5. It's a commutation because combination because I'm taking a group of 5. I don't care about the order of them because I'm going to rearrange them in my hand anyways. Okay, so I'm going to put this in my calculator. And I find out that there's 2,598,000. Oh, I have too many digits. 960 hands possible. Okay, now let's consider a particular hand. A flush in poker is 5 cards of the same suit. Suits are the little pictures. So hearts, diamonds, clubs, or spades. How many different flushes can be formed using a standard deck? Okay, I'm going to do it 2 very similar but slightly different ways. Okay, so let me see. Depending on which one I am, say I'm at hearts, there's 13 hearts to pick from. I want to have exactly 5 of them. Okay, so this is the number of combinations if I only pick a flush from the hearts, but there's actually 4 suits. So I could do 13 choose 5, and then I could multiply it by 4 because there's 4 different suits. And I'll see what this gets me. So there's 5,148 flushes possible, which when you consider the total number of hands in the deck is not very many. Okay, and that's one way to calculate it. If you prefer to use the formula all the time, the other way is I could say, okay, there's 4 suits to pick from. Okay, so of the 4 suits, I want to pick 1. And then once I pick which suit, there are 13 cards, and I'm going to select 5 of them. Okay, and I can evaluate it this way, 4 times 1287. Okay, and I still get 5148 flushes, but there is more than one way to set it up. The main thing is you need to show me how you set it up, and then you can use your calculator to evaluate.